professor at University College Dublin and is full professor in sustainability geosciences at the School of Earth Sciences. She received in geology from Trinity College Dublin and a PhD, so a bachelor from geology from Trinity College Dublin and a PhD in geochemistry from the Royal School of Mines at Imperial College in London. Professor Sarah Gleeson has broad research interest in mineral deposit genesis, hydrothermal fluid flow, and water-rock interaction. In her career, the focus of her research has been on the genesis and detection of base metal mineral deposits in sedimentary basins, with a focus on mineral system models, sedimentary geochemistry, diagenesis, and ore forming processes. So, within CRS career activities, so this is a research center at the level of University of Bucharest for counseling and orientation research, and we recommend to all of you to periodically look at the site of this center because it contains a lot of information of interest for you, even as a student, and the possibilities to get involved in various research activities in institutes and universities at the level of the region of Bucharest people. So within these activities organized by CRS Career, we are glad to have today this lecture of Professor Sarah Gleeson. So please, thank you.
Thank you. Thank you. Thanks for the introduction. And just to explain that I work at the GFZ in Potsdam in Germany until the 30th of June. And then I'm also now working in Dublin. So I'm the director of the Irish Centre of Research Applied in Geosciences. So right now I have 2 jobs for another month, but then the German job will stop and I will be fully 100% in Ireland, back where I started, which is really great. So the talk I want to give you today is about copper mineralization. And as a professor, of course, I don't do all the detailed work. So I'm actually giving you the results of my student, Mohammed. It's his PhD work. So really, he's the first author on this talk. So before I get going, I just want to do my acknowledgements first. I'm going to show you some stable isotope work from SIMS and some TEM images. And I'm going to show you some samples from a company that are drilling in eastern Germany, and also some historic core from, brilliant, thank you.
You are welcome.
Yes, some historic core from the surveys there. Okay, so let's start off with the question. Why do we care about raw materials and copper? Well, it turns out that copper is vital for the energy transition. So all the green technologies require vast amounts of metals, specialty metals. And so as we move basically towards carbon neutral societies, we're going to increase the demand of each metal. And of course, copper is excellent for transmitting electricity, and we don't have any substitutions for that metal. So for example, here you can see this is sort of the cars that most people are driving outside, I can see right now in Romania. But this is what the electric car will look like. And it will require a whole bunch of specialty, some of them in the batteries, but actually the rest of the car also requires specialty metals. If you think about things like wind turbines, they require huge amounts of steel and concrete, but actually they also require specialty metals like copper and rare earth elements to stabilize magnets, for example, in those windmills. So when you look at projections of where we're going, and you look forward to maybe 2030 or 2050, it doesn't matter sort of which kind of calculation you use, it's clear that we're going to need many more, much more metals than before, and that need cannot be met by recycling. So this basically means that we are required to mine if we want to build these infrastructures. So what kind of mines do we have for copper? So the biggest mines on the earth mining copper are these porphyry copper deposits. And this is a picture of the Bingham Canyon deposit in Utah, where they're basically mining 0.38% of the rock is copper, which means they're throwing away the rest of the rock, okay? And as a result of that, they have to dig ridiculously large holes. So this hole in the ground, people always show this picture because it's one of the biggest, but this is 3 kilometers wide. You can't get the sense of scale from this picture. So that's basically most of the copper that goes into your phone, your computer, your house, comes from a deposit that looks like this. If you're looking at sediment-hosted copper, which is what we're talking about today, those mines can look quite different, and that's because a lot of the mining can be underground. And it can be underground because the amount of copper in those deposits is much higher. So 2% of the rock is copper. And that basically means that you can use more expensive mining metals to get it out because you're still making a profit. So these deposits are an attractive target for exploration companies. So where do you go in the world to find these deposits? Well, they're actually not found in very many places, okay? So there are some really giant ones, and the most famous ones are here in the Central African Copper Belt. In Zambia and in the Democratic Republic of Congo. This is where they've been mining copper for many, many decades. And these deposits are famous because these deposits come with cobalt. And this is the largest source of cobalt on the planet, and we need cobalt for all those batteries for electric vehicles, okay? Then we have other areas, for example, in Kazakhstan, there's a giant deposit there. There's a big one in the US. But here in Europe, we have what are called the Kupferschiefer deposits. And for those of you who speak German, Kupferschiefer just means copper shale. So basically, it's a unit that contains copper. And those deposits are mined in Poland. And they're mined today. This is one of the Polish mines today. But historically, they have been mined in Germany. So finding these deposits is really challenging. And I wanted to show you this. So this is actually depth beneath the surface, and this is time here. And this shows when different deposits were formed or were found, where they were found. And you can see sort of between 1900 and 1940, a deposit had to be exposed on the surface. So generally, you know, somebody went out with a hammer, they hit the rock, they could find it. But what's happened over time is that a lot of these deposits at the surface have been found. And now people need to look in the subsurface to find deposits, sometimes down to sort of 500 meters. And these green dots here are some of these Kupferschiefer deposits. They're found really deep, and they were found by drilling by oil and gas companies who were drilling deep to find oil and gas, and they happened to find copper in there. So this is one of the challenges. If you want to go look for more deposits like these in somewhere like Eastern Germany, you've got to be able to see 500 meters under the ground, and this is a non-trivial issue. So in order to help the geologists and geophysicists figure out where to drill, if they think they want to do this, we develop what we call mineral systems models. And these are generalized models where we basically summarize in a cartoon what we think the main parts of the mineral system is. So for these copper deposits, they're formed in sedimentary basins. The sedimentary basins are in the middle of continents, intercontinental sedimentary basins. And it's thought that the copper is coming from units deep in the sedimentary basin. They could be clastic units, or maybe there's some volcanic rocks in here. And those rocks contain very low amounts of copper. So you have to pass a fluid through those rocks and strip the copper out of those rocks to form these metal-bearing fluids. And then basically these metal-bearing fluids travel up along faults, and those fluids are oxidized. They're carrying copper, we think, as chloride complexes. So these are brines that are carrying the copper. And when those fluids hit a redox boundary, in this case, this is a shale that contains a lot of organic matter, they precipitate out the sulfides as a layer normally in these basins. So you get metals from the basement, you have saline mineralizing fluids. Often we think that's the case because there are evaporites, things like halite in these basins. So we think there's water around with a lot of chlorine in it. That can transport these metals, and then they get trapped at this redox boundaries and they form these ore deposits. Ooh, what happened there? Okay, so where is the Kupferschiefer actually in the subsurface? Where do we see it? It's actually a really large unit. It goes all the way sort of through Poland, Germany, bits of all the way to the UK. So it's a unit that we know, it goes all the way across Europe, but it doesn't contain copper deposits all the way across Europe. Interestingly, the copper deposits, the really big ones, are here, and they stop at the German border. And over here we have things that were mined a long, long time ago, in sort of 15th century, some things, up until the 80s. But there's small amounts of copper mineralization over here, but the really big deposits are here. And so I'm going to show you, we're going to focus on this area here, which is where Mohammed did his PhD. And then I'm going to show you a few little examples of something sort of special from over here in Spremberg, where there is active exploration going on. There's a company there drilling for trying to find something for copper. Okay, so the Kupferschiefer district is located at the southern margin of the southern Permian Basin, and the mineralization occurs in a layer that's basically only 2 meters high or wide, but can go for 70 or 80 kilometers, so it goes really far. And it's in Permian age rocks, and what you have is you have these red bed sandstones down here, then you have a shale, so something that's rich in organic matter, and that's the Kupferschiefer, if you like, itself. And then on top of it you have carbonates, Zechstein aged carbonates. And in here, in this little zone here, if you blow it up, you've got maybe 2 meters, and this is where copper, lead, zinc mineralization occurs. So let's back off and just think about the geological setting of where these deposits form. So before these basins formed, we get these basin terrains which record complex accretionary history. This is basically where parts of the crust have hit together and they've become sutured, often associated with old mountain belts. So we have the Precambrian East European craton, which is Baltica, that's this yellow area here. Then we have the Trans-European suture zone, okay, and that is made up of the remnants of many of these mountain belts, the Caledonian, the Variscan, and the Alpine orogenies. Of course, the Alps are still with us today. And then you have this Rieck suture here, and this is sort of under where all these deposits form. And that separates a piece of crust known as Avalonia from Amarica, and it's there when the Rieck Ocean closed in the early to middle Carboniferous. So that's the basement underneath these deposits. And then what happened was rifting happened. So the crust began to pull apart, and the first thing that happened was you got some volcanic activity. So you get a little bit of magmatism here and some volcanic rocks ranging in composition from basalts to rhyolites, and they're sort of preserved here and there in the rock record. Then on top of that, you get these thick sequence of red beds. So sort of imagine this is like, you know, looking at somewhere like Arizona or somewhere like that in the US. These things are deposited in the German basin and the Polish basin here. And you've got these thick sequences, so it's arid, it's dry, there's a lot of windblown sand, there's maybe some rivers, and in places you get non-marine evaporites and different kinds of salts being formed. And this is the Rotliegend sort of succession that you find under the deposits, and this is also thought to be maybe the source of the copper in these systems. Then what happens is the ocean comes in all across Europe, something called the Zechstein transgression. The ocean floods in, so basically it comes from the north, people think, up here, kind of from the UK, and it starts coming across Europe, and it covers up all these red units, the fluvial, the Aeolian sandstones, and you end up with a sort of a sea here. And this is where these carbonaceous mudstones are deposited. So this box here is a zoom in. So you have an ancient shoreline here that's shedding sediments into this basin. And then you have areas where the water is deeper, but you have these little islands here as well that are still sort of sticking up. Okay, so when you look at the Kupferschiefer unit itself, sometimes it's absent. So for example, if you're on an island here, topographic high, you don't get the shale deposited. But if you're here in deep water, you might get quite a thick shale deposited, okay? So here you get the carbonates sit on top of the sandstone, there's no shale deposited. Over here you have an area where you do get a thick shale deposited with lots of carbon in it. This is a good reducing unit for redox reaction. Or you might get areas that have slightly thinner shales. And this is what the Kupferschiefer really looks like. On top of that, that's the first, if you like, the first ocean came into, flooded across Europe. And then that ocean developed more, got deeper and deeper. And you start to make limestones. And also, eventually, that ocean began to dry up, and you made all these big salt deposits. And actually, in Poland, in the mine that I showed you at the beginning, they're mining copper at about 1,000 meters below the surface, and 150 meters above the copper, they're mining salt. Okay? So you mine salt and potassium salts for fertilizers. So they're kind of doing both things in the same mine. Okay, so you have this sequence of these sandstones down here, and then you basically have your shale, which is the first expression of this marine transgression over Europe, and then you get into these limestones up here. And the mineralization is found where this redox boundary occurs around the area of this Kupferschiefer. But the mineralization is not just in the Kupferschiefer. It actually occurs in the sandstones underneath and also sometimes in the limestones on top. So it forms in this, often it's a 2 meter or 1.5 meter zone, but you can get mineralization in sandstones, in shales, and in limestones. And so people have argued that there's a zonation. So the fluids are passing through the basin. At the bottom, the fluids deposit something called the rotifaula, which is a hematite alteration, which tells you the fluids are oxidized. Then you get a copper zone, and then as the fluids pass through the basin, the mineralization changes from copper to lead to zinc. And then you get pyrite, which is not of any economic interest, sort of on the edges of the system. So these deposits have been known for a long time, and there have been arguments about when they formed, okay? So some people think that actually the sulfides formed in the ocean itself, a bit like a black smoker, and that you basically had the sulfides forming in the water column, and you got this layer of sulfide then on the ancient seafloor. And people have sort of argued that because when you look at the rocks, the bright white stuff here is the sulfides, and it sort of occurs in layers. So that was sort of one idea. And the fact that maybe this mineralization is early, it was supported by sulfur isotope values in the sulfides. So you can measure the sulfur isotopes in the sulfides, and they have these really negative values. And that's telling you that the sulfide is being generated from seawater sulfate by bacteria, okay, at really low temperatures. Bacteria basically metabolize the sulfate, turn it into sulfide, and that sulfide is being used to form the copper mineralization. Other people think it formed later in the basin history, when the basin was being buried, maybe not in contact with the open ocean again. And they argue this on the basis of textures. So for example, these are rhomboidal pyrites, which are formed early, and they're all through this rock in this basin. But the blue stuff, this is the copper sulfide chalcocite, and it's replacing the rhomboidal pyrite. And in fact, in the sandstones underneath the deposits, you can see grains. For example, this is a feldspar grain, and it's being replaced by chalcopyrite. So you can clearly see that the sulfides are taking out the feldspars here. So this would be happening later on in the basin history. Now, there was a very important study that was carried out quite a long time ago. And what they did was they took a bulk sample of the rock, and they separated out the mineral illite, which is basically a low temperature phyllosilicate. And then they used dating methods, potassium argon, to date the illite in the rock. And they got samples away from the mineralization, just anywhere. And then they got samples in the mineralized zone in Poland. And what they found was they got this whole range of different geological ages. And these ages here are probably the age of the deposition in the basin, okay? So, and maybe even some older ages of things that have been inherited in the basin. But these ages here are probably the ages of the mineralization. So they suggested that the mineralization was maybe 245 million years ago, and therefore that it happened after the sediments were laid down and after, burial had started. And that was quite an important study. The trouble was that certainly back then in the 90s, you couldn't, it's a bulk analysis, so you can't really be sure that this illite is something to do with the mineralization. Now, I'd spent a lot of time talking to people that work in companies, and basically academics like to argue about these things, right? And so, like, if you actually want to go out and find one of these deposits, does this matter? These details, do they matter? So if it's formed sedimentarily or deeper in the basin history. So it does matter, actually, because the deposits that people could be looking for today are at sort of hundreds to maybe 1 kilometers deep. And typically, we would rely very heavily on geophysics to image these things in the subsurface. Now, imaging the Kupferschiefer is challenging because it's this thick. Okay, so at 500 meters, identifying a layer this thick is a non-trivial issue. The other issue is that the basin on top of that mineralization is full of salt. And all the fluids in the basin are full of salt, which means things like electromagnetic methods are going to image salt, because we know salt is conductive, right? So it's actually quite difficult to explore in this sort of situation. So therefore you have to have a conceptual geological model of where you might want to put a drill hole. And so if it's sedimentary, then you're looking for sedimentary faults and areas where you might have H2S in the water column, which means that really you're looking for the Kupferschiefer itself. If, however, you're thinking that the mineralization is diagenetic, maybe formed a bit later in the history, then you're looking for any structures or areas of paleofluid flow which connect the metal-bearing fluids with any H2S reservoir, and that could occur in any unit. So basically this opens the search space, okay? But one of the questions is, if it's forming later in the basin, how can you effectively get those fluids, you know, through the basin for 60 kilometers to make these copper deposits? If the rock is already compacted and cemented, it's difficult to do that. The other question for the companies is, if you drill a hole and you don't hit copper mineralization, is there any mineralogy or alteration in that hole where basically you could say, yeah, I'm in the right area. Maybe if I drill another hole 100 meters over here, I might hit it. Okay, so they need hints. It's kind of detective work, really, to figure out where to go next. So enter Mohammed, so his PhD. We looked at the Sala subbasin, and really there were two questions. One is, what's the timing of the copper sulfide mineralization in relationship to the diagenetic phases in the basin? And we wanted to know, these systems have no fluid inclusions, which means that you're always guessing what the fluid chemistry is. So we wanted to know, could we see any constraints on the salinity? Could we really show that the metals are being moved by chlorine-rich brines? So this is the Sala Basin. Down here, there's Berlin, and we're kind of down here. And he had access to only 3 drill cores, here they are, from the Sala Basin. And this is what they look like. So into the Rottliegendes, the sandstones and conglomerates underneath the Kupferschiefer. Then the Kupferschiefer, which is carbon rich at the bottom, but becomes more carbonate rich towards the top, and then into the limestones that sit on top. So one of his holes had copper mineralization and a little bit of this hematite alteration underneath it. Another hole had a bit of copper mineralization, but more lead and zinc mineralization, and the third hole just had lead and zinc mineralization. Okay, so before we talk about those holes, I'm just going to go back and talk a little bit about this issue of alteration and trying to identify alteration. So we have an EU project which finishes up at the end of this month called Vector. And one of the things that was carried out in that project was we wanted to see if hyperspectral imaging could be used. If you scan drill cores, can you identify minerals that could be useful for exploring in these sort of situations? So this is work that was carried out by Sam Thiele and the Helmholtz Institute in Freiberg. And this is the scanning system. So this is a system whereby they've got 3 cameras. You can put your boxes of drill core through the system, and the cameras record spectral information in every pixel, okay? And you can put all this into a container and you can ship it to the site. So this container came to Eastern Germany, not so far from Freiberg, but it was also sent to Ireland to ship or to scan rocks in Ireland as well. So it doesn't work for all minerals. You can't make a scan and say, I just want copper minerals. It doesn't work for sulfides. But it does work for other minerals, like things like illite, epidote, muscovite, hematite, the minerals that you might find in alteration assemblages. So what they did was basically they scanned about 7.8 kilometers of core in this project. And you know, you're collecting multiple spectral signatures every 1.5 millimeters. So this generated an absolutely obscene amount of data. And then you have to basically figure out how to process that data. So Sam wrote a whole bunch of Python scripts. For example, you have to remove the wooden box from the data set. There's a whole bunch of automated scripts. And what we were trying to get out at the end is to turn these spectral signatures into mineral abundances so we can make a map of the rock. And so this is, after a lot of work, lots of machine learning, this is the product. This is not easy, let me assure you. And so this is what it looks like. So what he's done here is he's put families of minerals together. And this is drill core. And here, this is the Kupferschiefer itself. And the Kupferschiefer doesn't contain a lot of minerals that are hyperspectrally active. So it looks kind of black. But what you basically see here, these are the minerals: quartz, potassium, feldspar, and plagioclase. And they're basically making mineral abundance maps in the core samples. So you can see that these samples here in the Rotliegends, the sandstones that sit under the deposit, contain lots of quartz and feldspar, which you'd sort of expect. And you can see that sitting on top of the sort of potential ore horizon, there's still some units that contain quartz and feldspar in it. The next one is anchorite, dolomite, calcite. So these are carbonates, and some of these are minerals you'd expect to see in a limestone. And of course, we have limestone sitting on top here. And yes, we do see these minerals, but you do see some changes in mineralogy above the ore zone. These different colors represent different mineral abundances. Then we have kaolinite, muscovite, and illite. And these are the most interesting ones because there's actually all these color changes suggest that there is some complexity around the ore zone, and maybe that might be useful for exploration purposes. And then we have copper sulfides, halite, and sulfides, or sulfates, but unfortunately this is all anhydrite cement. So this is sulfates that we're imaging here. But I want to go back to this because this illite is important, basically because the problem with these scanning techniques is they map every event that ever happened to the rock. So we're seeing everything that ever happened to this rock here. We're not just seeing the events associated with the mineralization. Okay, so we see detrital phases, orthogenic phases, there's probably hydrothermal phases in here, and post-hydrothermal overprints. And what we really want to know is, if we look at something like illite, can we tell if there's illite associated with copper mineralization? And that's what Mo was trying to do. But before we start that, let's look at some pictures of what the rocks look like. So if we go into the Rotliegend sandstone, okay, and this is the sandstone underneath the deposits. These are the clasts, and it's got this calcite cement. And these bright phases here, this is the copper sulfide bornite. And the bornite is replacing this calcite cement. And here's a grain that we have also. You've got calcite left in here, so there was calcite cement once upon a time in this rock, and all this bright stuff here is copper sulfides. It's replacing the calcite cement, but it's also replacing these K feldspar grains, just like I showed you in the earlier picture. Okay, and we can make maps of this, and you can see basically this is all the copper mineralization here. In the Kupferschiefer itself, in the unmineralized Kupferschiefer, this is what you see. You see a really fine-grained rock. It's got organic matter, these black sort of parts here, it's organic matter. You get these coarser-grained lamination, and a lot of them are carbonate cemented. Okay, so there's dolomite, there's calcite in these laminations. In the mineralized zone, you see the copper sulfides take out those coarser laminations that have the carbonate cement. So, the fine-grained stuff doesn't have lots of copper in it, but all these sorts of areas here are replaced. So in other words, the copper mineralizing fluids are dissolving the calcite cement and precipitating the copper in the same areas. If you go into the limestones on top, the mineralization looks a bit different, and that's because the limestones are, it's easy to dissolve a limestone. So you actually get holes in the limestone that are full of these copper sulfides and pyrites, and you can make a map and you can see basically the bornite here, very well developed in places in these limestones. So in the three rock types, it looks like the copper sulfides are replacing carbonates. But how do we know it's all the same age carbonates? Okay, so it's always a good thing to check. So what we did was we did microprobe analysis to look at the chemistry of the carbonates in the three units. And the answer is yes, more or less in terms of the major element chemistry. The carbonate in the sandstone and the carbonate cement in the Kupferschiefer and the carbonate cement in the limestone are the same composition. So we wanted to go a step further and look at the isotopes in that carbonate cement. Now, these rocks are really fine grained, so they're difficult to work at. So you can't do sort of some of the more traditional isotopic analysis. So you have to do in situ analysis with secondary iron mass spectrometry. So this is 100 microns here, okay? And you're using a SIMS, and these are the spots that the SIMS analyzed. The red are the carbon isotope results, and the blue are the oxygen isotope results. And you can see this is in the sandstones where you have nice cements developed. It gets a lot more challenging in the Kupferschiefer to find a place to put your beam, but we found some places to do that. So the data that we got are really complicated. Okay, so this is a plot of the carbon isotope composition against the oxygen isotope composition, and this is in the sandstones and this is in the Kupferschiefer. You see we have a lot less data in the Kupferschiefer because it was much more difficult to analyze. And what you see is there's quite a wide range in carbon isotope compositions in both. And in the sandstones, there's a very large range in oxygen isotope composition. So this isn't telling us that there's one fluid here that made this carbonate cement. It's telling us there's multiple sources here. So probably the alkalinity for the calcite cement comes from a mixture. This is a brachiopod, which is a fossil, and that's supposed to be representative of the ocean water in the Zechstein Sea. And down here, this is what happens when you have organic matter or decaying organic matter. And so probably the carbon is coming from a mixture of both those things in this system. And the oxygen isotopes basically can be interpreted that there's some meteoric, there's some rainwater getting into the reservoirs here, but also maybe some evaporitic fluids that have been evaporated and have sunk into the basin. And also you're probably seeing alteration of the clasts here, and that's why you're getting this really wide range in oxygen isotope values. Now these sorts of complex situations are very typical of the values that you get in cements in early diagenetic reactions in sedimentary basins. Now, one of the things to note that's interesting is this background variability in the isotopes is not being overprinted by the mineralization. So the fluids that are carrying the copper do not have, maybe there's not enough of them to actually start resetting the local isotopes that you find in these sandstones. So back to this issue of the illite. So we know now that the copper is coming in after this carbonate cement and it's dissolving it as it travels through the basin. But what about this mineral illite? And can we prove that there is illite that formed with copper sulfides? So now we've got to go down to smaller scale again. So this is now transmission electron microscopy. And this is one of these sandstones. And here, Mohammed has taken a slice. This is a focused ion beam section here, across here from this grain into this pore space where the cements are. And this is the slice here. And when you zoom in, what you see is you see pyrite. And here's boronite, our copper sulfide. And I don't know if you can see this, but all these sort of little bladed textures in here, this is the illite. So this is completely convincing evidence that yes, illite is formed as a mineral at the same time as the boronite. They're co-occurring here together. Now, sometimes you send your PhD students off to answer one question, and the question was, is the boronite coeval with the illite? And they come back and they've found something completely unexpected and wonderful that you really hadn't predicted. So while he was doing his TEM work, Mo took another slice over here. There's boronite sitting in a pore. He took this slice here. This is zooming in. Now we're down at 200 nanometers, right? We're getting smaller and smaller and smaller all the way through. And here's the illite. So it has this sort of morphology here. But there's these bright white zones, which you shouldn't see in illite. And when you analyze this with EDX, it turns out this is copper chlorides, hydrated copper chloride ions inside the illite. We were like, whoa, well, that's interesting. So then you go down in scale again, 20 nanometers, 4 nanometers, and actually inside the illite, there are nanoparticles of copper chloride formed. And so some of them are just copper chloride phases, but some of them are also something that's recognized as a mineral, and it's a mineral called atacamite. Now, do you all know where the Atacama Desert is? It's in Chile, right? It's one of the driest places in the world. And the atacamite forms because some of these big porphyry deposits that I showed you earlier on, some of our biggest porphyry deposits are formed in Chile. And this is what happens when copper mineralization meets the oxidizing atmosphere. And you form this weathering mineral. It's green, and it's called atacamite. So actually, inside this illite, there's also places where you're seeing this mineral atacamite, and you can do crystallography to confirm the composition of the mineral. And actually, that's what atacamite looks like if you found it outside on the surface. So, some of these phases have been described before. But people thought they were in the rocks because there are all these salty fluids that are currently, even today, circulating around in these basins. So they thought maybe the metals were being leached by these groundwaters today that are full of chlorine, and that's what's forming these sulfides. But we've really shown that these copper chloride phases are associated with both boronite and these pore filling illites. And so what we're suggesting is that actually the illites, because the illites have a positive charge on their surface, that they're actually attracting negatively charged copper-1 chloride ions, and they just get stuck there, basically, in the mineral for us to come 250 million years later and analyze with our equipment. Still always amazes me. Now, what we know about atacamite is that at the surface, atacamite is a low-temperature mineral, so this is more supporting evidence that the Kupferschiefer was a really low-temperature system, maybe at 110 degrees max, but really happening at low temperatures. So, just to summarize, we're at the end. So the Sala Basin has an early diagenetic carbonate cement. That cement is found in the sandstones, it's found in the Kupferschiefer, and it's found in the limestones. The mineralizing fluids pass through the basin. They dissolve the cement and also sometimes feldspar clasts, and that controlled the lateral fluid flow of the copper mineralization. Because we found those nanoparticles in the illite, we now can say with confidence for the first time, for sure, that the mineralizing fluids were low temperature, probably under 100 degrees. We know they were oxidized brines because they do make this hematite alteration. And the copper was complexed as a copper-1 complex in the fluids. Then the mineralization formed when these metal-bearing fluids reacted with a reservoir, or actually 3 reservoirs, that contained hydrogen sulfide. And that hydrogen sulfide ultimately came from bacteriogenic sulfate reduction. And one of the things that's interesting here is that if you do drill a hole in the Kupferschiefer, and you're trying to figure out now where to drill your next hole, that actually mapping out the carbonate, because that's the path the fluids took, but also trying to map out the illite distribution in 3 dimensions might actually help you understand more about your system and where you could go next to explore. And that's all I have for you today. Thank you.
So thank you very much for this very interesting and provocative presentation. Of interest for us because, as you say, copper is important in a lot of industrial applications. Please, if there are questions,
any important byproducts that are found alongside copper?
Well, so one of the interesting things about this system is I mentioned the copper belt, and the copper belt has got, that's where most of the world's cobalt is. There's no cobalt in these deposits in Poland. And we don't really understand that very well. But there are other byproducts. So the alteration underneath, basically this red hematitic alteration sometimes has gold in it, and sometimes it has some platinum group elements in it, and actually, but they don't extract those in Poland. There's not enough of them they can do anything with them. But they do actually take silver out of these deposits. So silver, other than jewelry, the big use for silver is actually solar panels nowadays. This is the growing market for silver. So this deposit also has some silver that they do actually process. But all the rest of the metals, they don't recover. Yeah, it's always such a waste in some ways, but yeah.
I was wondering if in the other sediment-hosted ore deposits, is the same dilemma of syngenetic versus diagenetic orogenic?
Right, well this basin is young, because it's only 250 million years old. The Central African Copper Belt Basin is much, much older, and it's been through multiple phases of metamorphism and deformation. And what's become clear now in those systems with better geochronology is that the copper mineralization does happen at multiple times in that basin. And we don't see it happening at multiple times here. It still looks like one event here. But in the really old basins, there's more time. If you think about it as there's a copper source and there's a trap, a chemical trap, and all you need is to connect the fluid flow pathways. And so the question is, can you do that more than once in a basin history? And the answer is clearly yes, you can. So if you kind of believe in that sort of petroleum systems model, yeah. So there are these debates, and for a long time, people would argue so strongly, it has to be, it's younger or it's older at conferences. But now with geochronology, you can take a single apatite grain and you can see, the older mineralization age in the core and the younger mineralization age in the rim. It's amazing, yeah.
And also, another question, can we pinpoint the source of the metals?
No. No, this is always the big challenge. We know they come from somewhere down there, but because those rocks aren't exposed, there's never really a rock you can put your finger on it and go, the copper has been stripped out of this rock. It's quite challenging. There are some other systems, where things have been tilted, where maybe and exposed, and maybe you can sort of do those sorts of things. But this has always been one of the challenges. And people have tried maybe doing, when you do copper isotopes, it tells you about redox changes in copper, but it doesn't tell you really about where the copper is actually coming from. So it's a challenge.
Maybe the lead isotopes, would that help?
Yeah, people have done lead isotopes, and I mean the lead isotopes, tell you that you're coming from the red beds or from the basement, but it doesn't tell you anything more specific than that. Yeah.
But even talking about, I don't know, maybe the geographical thing, you see some intrusions in that by using seismic or,
right.
graph or magnetometry and stuff like
yeah.
that.
So we don't see anything like that here. But in the copper belts, because the copper belt in Africa has been understudied, it's a logistically difficult place, there's beginning to be an appreciation that there's more mafic magnetism around. And of course, mafic magnetism would bring nickel and cobalt with it. So maybe this is where the cobalt comes from there. But there's no such, major intrusions here. It's too young at this time. Yeah.
Some other questions?
Just a comment.
Please.
That was a fascinating presentation, so rich in methods and information. And if I understood correctly, the mineralization doesn't have fluid inclusions?
No.
No.
No, because you don't really.
Is this useful information? I mean, we can.
So the mineralization is really, really fine-grained. And these, we did look at the carbonate cements to see, could we see any fluid inclusions? And if there are fluid inclusions here, they're so tiny, you can't. And you don't get veins where you get nice fluid inclusions developed. You do get veins in this basin that are later, and maybe alpine age veins. And there is copper mineralization in those veins, but they're telling you about a different event. They're not telling you about this major event. So this is always one of the problems, because we love fluid inclusions because they really help us identify the temperatures, the compositions, and then maybe you can analyze them. But in these fine-grained deposits, it's always a challenge, because they're just not there.
And maybe I would stress on the fact which you illustrated here, what an adventure the scientific research can be.
Yes, it's always a good day when somebody comes into your office and shows you something you never even imagined could exist, and that's the fun part of it. There are other days, that aren't so fun, but that's a really wonderful moment. And we really rely on our graduate students for this, because, I do not have the time to be sitting there looking down the microscope. And so you guys get to have all the fun, really. That's, and you have some time, which is a very valuable commodity. Yeah.
Okay. If there are no further questions, please.
Thank you.